write on paper number 22 titled ADA-VIT Vision Transformer for Detecting Diabetic Retinopathy. I take the privilege to welcome Prameela ma'am onto the stage.
Good morning everyone. This is Prameela. Actually, I am a government lecturer in Polytechnic. I am working as a senior lecturer in Government Polytechnic, Kadapa. At the same time, I am doing my PhD in ADA-VIT University, okay, under the guidance of Dr. M. Kamala Kumari.
Which university?
ADA-VIT University, Rajahmundry, sir. Rajahmundry. Good morning to Prabhu sir, and I thank this institution for giving me this opportunity to have a speak on, to give a paper note. Okay, my thesis is on the effect of different diseases, okay, using deep learning and machine learning techniques, and in that part I have come here to give a speech or to publish my paper in diabetic retinopathy that uses the vision transformers along with adapter Roy algorithm. Okay, basically during my thesis I worked on different diseases. In that part I am working on the effect of diabetes on different organs. One of the paper is the effect of diabetes on heart disease, and this is the effect of diabetes on diabetic retinopathy. So basically why we are dealing with diabetes in this today's world, and according to WHO, I mean World Health Organization, diabetes is the major disease which affects every organ. Okay, so in that part, diabetic retinopathy basically it affects the eye disease, eyes. Okay, so it affects the retinal part. Usually if the eyes are affected, basically we go to an eye doctor, ophthalmologist. The eye doctor, he takes the CT scan, everything, and he checks that. Okay, so while checking that, the doctor has to keep on checking that. Means when the patients are more, you know, the doctor has to check each and every scan, and when the patients are more, there is a chance that he may overlook. So in that case, the artificial intelligence and machine learning plays a role. Why artificial intelligence is playing a role means, see, so in diabetic retinopathy, the early detection is very, very important, because if we detect the diabetic retinopathy early, then he can go for the treatment. Okay. So my paper deals with diabetic retinopathy in a machine learning way. In that I am using a deep learning technology called vision transformers. So in detecting that I am using an optimizer algorithm called adapter Roy optimizer algorithm. Okay. So in diabetic retinopathy, there I have to give a few introduction about that diabetic retinopathy. Basically it has soft exudate, hard exudate, microneurysms and hemorrhage. What is soft exudate? Soft exudate means it is a cotton wool like thing, and we find a small patches over there. Those come under soft exudate. And hard exudate is nothing but a pale yellow thing. Okay, it is made of lipid and protein thing. Okay, and microneurysm is a very small tiny swelling, and hemorrhage is leakage of blood. Why I am telling these things means, to detect or to predict the diabetic retinopathy, depending upon these things we'll predict. So diabetic retinopathy is basically divided into 4 types: mild, moderate, severe and proliferative. Mild, as I discussed in the previous slide, microneurysms. Okay, they are small patches. When the diabetic retinopathy detects those, it means it is mild. Okay, and moderate means the blood transportation, you know, the nerves becomes very loose and the blood transformation goes. And severe means blockages in blood vessels that occur and gives a signal to grow in blood vessels. Proliferative is the very advanced stage of diabetic retinopathy. So my research, okay, basically it is the methodology, it consists of input images, pre-processing, lesion segmentation, optimization, and detection of diabetic retinopathy severity. So the input images I have taken from the IDRID data set, and for pre-processing I am using non-local means denoising. Okay, I will come to that section in detail. Okay, and lesion segmentation I am using MSegnet. For optimization I am using the adapter drawer algorithm, and for detection of diabetic retinopathy I am using vision transformers. Okay. My previous session, Jain sir, I think he has given a very excellent session, okay, on the basics of this deep learning techniques and optimization techniques. I will be using some of those techniques in my paper also. This is the architecture diagram of mine. So basically the database, the IRDRI database, okay, I am taking that, and for pre-processing I am using the non-local means denoising algorithm, and from non-local means it goes to the lesion segmentation. Whatever I told, microaneurysms, soft exudates, hard exudates, and hemorrhages, in the lesion segmentation I will be classifying those things, and from there feature extraction. From feature extraction it goes to the vision transformers. Before going to the vision transformers, my adapter drawer algorithm, it generates the weights and gives those weights to the vision transformer. Okay, and vision transformer detects whether the diabetic retinopathy is mild, apparent, severe, or proliferative or moderate. So NLMD. So as I told, NLMD, non-local means denoising. Basically the denoising algorithms, they use local weights. So I am using non-local mean. In the name itself it is saying that non-local means. So when a pixel is there, okay, it takes the average of the neighboring pixels also. So it takes the mean of those things. So that is given by the formula there. So if A of phi of psi, A of phi is the pixel, W is the weight. Okay, so that takes the summation of all the neighboring pixels also. So in my output I will be showing, because of that space I have given, I will not show the output over here. In the output section I will explain those things. And the MSegnet. MSegnet is it uses both CNN and global attention. So I think many of you are aware of the CNN, or else I will tell you. Okay. So this section contains two blocks, encoder block and the decoder block also. So the encoder block, it has one convolution layer 1 by 1, and it uses ReLU, that is rectification linear unit. Rectification linear unit, you know, it takes, if the values given are minus values, negative values and up to 0, the values taken as 0, and if the values are greater than 1, it takes the value 1. So that is the rectification linear unit we will be using there. Oh, it is okay. So the encoder block, as I told, and it takes the max pool also, 2 by 2 cross algorithm, and it is combined with the connection. That means it is appended, concatenation is being done. Okay. So if I say encoder block, basically that is the main process of the segmentation. Okay. So the encoder block, it takes the output of the previous layer and it is multiplied with the convolutional kernel, and with that, for that the bias is being added for that. Okay. So the output of the convolution model is downsampled to a 2 by 2 max pooling with a stride of 2, and that is given to the global attention thing. So okay, the global attention thing is nothing but a self attention mechanism that performs segmentation efficiently by removing the irrelevant features. The output of this module is given to the element wise addition. So, okay. So as I said, the global attention module, okay, it takes the output of the encoding process, because the image is being downsampled, okay. So after downsampling, it is given to the global attention module. There, again the convolution layer takes place, 1x1 convolution layer takes place, okay, and that output is being concatenated, and then for the decoding process, it is again will upsample the image whatever it is taken from the global attention model, okay. So in this state, okay, if the input is given the image of the eye, the output it will be detecting whether it is microorganism, hard exudate, soft exudate, okay. So from there it is classification is being done. So from this diagram, so after the segmentation is being taking place, we will come to the feature extraction. In that feature extraction, all the features like smoothness, uniformity, okay, there will be, I am taking those features. From there the vision transformers, it will come to the vision transformers, okay. So basically vision transformer is a combination of the encoder block and the decoder block. So in the encoder block we have multi-head attention network and the feed forward network, okay. So in this basically the multi-head attention network is nothing but a group of self-attention networks, okay. So how a self-attention network works? So for a self-attention network we should have basically a query, okay, a key and a value. The query is nothing but what question we are posing, key is the main criteria and what output we got, okay. So the notations query, key and value, Q is the information being looking for, K is the context or reference, and V is the content that is being searched. For example, in a YouTube if we search for a, if we give a search, okay, or like what is vision transformers, okay. So what is vision transformers becomes the query, and it gives the so many outputs related and not related to the query we have given, okay. If I given vision transformers, it sometimes it may display the transformers in the electric field also. At the same time it will be displaying the transformers image of a movie, transformer movie is there, right. So that also it been displayed, and at the same time vision transformers also will be displayed in the search. So what value what we require, okay, that is the K value, and the content that is searched is the actual V value what it is required for us, okay. So first what is self-attention module? So we need to identify the patches, how similar is each key to the desired query, and that is nothing but the attention mask we say, okay. And then we have to extract the features with high resolution, that is written the values with the high resolution. So how self-attention module works, okay. So self-attention module, how it works is when we give the image, okay, see when we give the image it is divided into patches, and each patch we have to create or develop a positional embedding. So how a positional embedding is being done, okay. So for each step, for each patch we have to calculate a positional embedding information. So how it is for, I will give an example for a string. For example, this is a room, okay, that is converted into a 2x2 matrices. This is a room and this is a room. In the 2x2 matrix, for each thing, okay, how it is the positional values they are updated in a matrix. So those positions have to be embedded, okay, and so those positions will be created in a array like this, okay. And those position embedding, okay, from that we have to extract the query, key and the value. As I said, query is the on what we are searching, what is the query we are giving. okay, and what value it is converted and what value it is given, okay. So with this we have to calculate the attention weight. Attention weight is nothing but the similarity between each query and the key. So similarity between each query and the key is nothing but we have to calculate the cosine thing, okay, cosine similarity. For that the formula is A and B. Here A and B is nothing but we will be calculating the dot matrix, okay, dot product between the matrices. So then dot product is being calculated, that is nothing but the matmul, and then we have to scale that, okay, and the extracted features will be with a very high resolution, and then softmax will be applicable on this, the whole thing. So Q is the query, K is the search thing, okay, key value, and the dot matrix between dot multiplication between K and Q is being done, and that is being again multiplied with the value which is given, and on this we will be applying the softmax algorithm, okay. Softmax operation will be being applied on this. Each multi-head attention layer is, each is a self-attention layer, and there are so many self-attention layers on this, and from there the feed-forward network is be given. And in the feed-forward network, whatever the query and the key value will be given again to the output of the decoder. This is the encoder block, this is the encoder block, and this is the decoder block. From the encoder block, the output of the query and the key again they will be given to the input as the multi-head attention network, and this output, okay, again from the output encoding also, decoding also, the position encoding will be being done, and the multi-head attention will be takes place, and from here the value whatever the here it is there, it is the value will be taking, okay. So in this way, the patches, the image will be divided into patches, and each patch will be going to the transformer, and actually the transformer what I have given there, okay. So this is the what internal process will be going done, okay. So for my thesis work I have taken the adaptive drawer algorithm. It determines the input is again whatever the image has been taken, okay, and it is in the form of lower value, upper bound and lower bound, and okay, and the will calculate the drawer matrix. So in the drawer matrix what it takes is the adjacency of all the matrices, you know, it will be calculated, okay, and again from there we will take what is R and T. R is nothing T is the total number of transactions, okay, iterations. T is the total number of iterations, and R is the index from which iteration we are taking in, okay. So we will calculate each and everything and will update it in the matrices. That is nothing but the drawer matrix, okay. How will make it adaptive is using a formula called this one, by applying the adaptive matrices, okay. The random number which is considered, you know, using this formula 5 into R max by 100, I am making this, it is the adaptive drawer algorithm. So the iterations, you know, until the optimal solution is acquired, this iteration keeps on running, and these weights are given as the input to the transformer. So with that weights, okay, the image being classified as mild or proliferative or severe. So these are the results which I have given, which I have got. I have compared with the deep learning algorithm CNN and okay, and this is the proposed algorithm. So if I am taking the training set as 75%, these are the results I have gotten, okay. So as I told, in the screen it is not visible clearly. If this is the original image, okay, so after pre-processing, I told that NLMD, non-local mean denoising algorithm I have applied there. Okay, so here it is not visible, but all the patches, what are all the patches are there, they will be removed from that, okay, and the clear image will be given here, and from here after MSegnet, the MSegnet I have used. So that is the output of this. Here it is not visible. Actually, microaneurysms is, I told it's a very, very small patches. Okay, so small patches are not visible over here. So from there, that output is given to the vision transformers. So vision transformers classify that it is moderate or mild or proliferative or severe. So depending upon this, it is the output is given as moderate diabetic retinopathy. Okay. So conclusion is, I am using for denoising I am using NLMD, and for segmentation I am using MSegnet. From that the output is given to the transformers. Okay, so transformers, vision transformers, it classifies that diabetic retinopathy is mild, proliferative or severe. My accuracy with this proposed algorithm, the accuracy is 0.87%, okay, sensitive is 94% and the specificity is 91.6. So these are the results when compared to other algorithms. My proposed algorithm, it is given the high accuracy when compared to CNN, okay, transformer-less perception model and everything. Okay. Right. So thank you. So any doubts? Sir.
The last results you mentioned accuracy, specificity and 3 things from
Right.
it.
Yes, sir.
Can you please please go through the previous slide. Okay, last.
Yes.
Anyway, you mentioned 3 things, madam, accuracy and
Yeah, right.
so what is the exact differentiation among those 3 quantities, madam?
Yeah, actually it's the
Sensitivity and specificity.
right. Accuracy, that will be calculated from the confusion matrix actually. That I have not given over here, okay. Accuracy is nothing but the true positive, whatever the true positive values we have got by the true positive and the true negative values. That is the accuracy. Means true positive is in the sense actual, what is the positive number of cases and how many of the positive cases our model has correctly predicted, that is true positive, okay, and true positive by true negative plus true positive. So true negative is the total number of negative cases in that our model, how much it has actually predicted correctly as negative, that is true negative, okay. So true positive by true negative plus true positive gives the accuracy, okay. Sensitivity gives true positive by false positive and false negative. False positive is in the total number of positive cases, how many cases our model predicted negatively. Means if it is diabetic retinopathy, our model it is predicted it is not diabetic retinopathy. So how many cases it is predicted negative cases, that is false positive. One is true positive, means predicted is true and the actual is true positive. True negative, predicted is actually it is negative and the predicted is also negative, that is true positive and true negative. False positive, actually it is true and our our model has predicted false. False negative means actually it is negative but our model has predicted as positive, okay. Actually I have to thank you for telling me that so that I can update in the next in the results. So with that values, those are mapped through a confusion matrix. We call it as a confusion matrix. From that confusion matrix only, we will get the accuracy, sensitivity and specificity. Thank you, sir. Thank you very much. That is specificity. From that, false positive by true positive plus true negative. That is the specificity.
Okay, thank you.
Thank you so much, sir. Thank you. Thank you.
Thank you, ma'am. That was a very engaging session.